Hi everyone, welcome to our WiN webinar. It's Nuclear Science Week. And first, I would like to begin by acknowledging the traditional custodian of our lands on which we meet electronically today, and pay my respect to elders past and present. I extend that respect to Aboriginal and Torres Strait Islander peoples here today. Today, I am located on the lands of the Harwell speaking people. We will start today, but first I would like to acknowledge our fantastic sponsors, especially ANSTO, Cyclotech, Gamma Gurus, GMS Australia, and Redtronics for the support in keeping our nuclear and radiological science community connected. Just to let you know that today's webinar will be recorded. We cannot see or hear you, but you can ask questions at any time via the Q&A button. We thank you for joining us today, and we value your feedback, so please send us an email at winaustralia@gmail.com. I'm Patricia, and I'm the Vice President of Women in Nuclear Australia. And today we are joined by Dr. Ceri Brenner, who's leader of the Centre for Accelerator Science. At ANSTO, Dr. Ceri Brenner leads the Centre for Accelerator Science, which is Australia's research infrastructure platform dedicated to ion beam accelerator applications that enable research and innovation communities to explore the past, understand the present, and design solutions and technology for the future. She oversees a team of scientists and engineers who support academic and industry users across Australia and the world with a suite of ion beam instrumentation for ultra-sensitive analysis, characterization, and irradiation applications that drive forward knowledge, innovation, and uniform policy in areas such as environment, climate, and health sciences, space technologies, advanced energy, nuclear and quantum materials, and cultural heritage. Prior to starting at ANSTO earlier this year, Ceri spent over 20 years at the Harwell campus in UK, first as a PhD student and eventually as group leader for industry partnerships and innovation at the Central Laser Facility, which is UK's user facility for high power and ultra short pulse lasers applied for fundamental and applied research in physics, chemistry, material science, and biology. She is a laser plasma physicist who specialized in novel and generation concepts for proton and ion acceleration from petawatt laser interactions with matter. She first visited ANSTO in August 2018 during her national tour as 2018 Australian Institute of Physics Women in Physics lectureship recipient. In 2017, she received the UK Institute of Physics Clifford Patterson Medal for exceptional early career contributions to the application of physics in an industrial or commercial context. So today we are really thankful that Ceri could actually take us on her career journey. And Ceri, I will hand it over to you now. Thanks so much.
Excellent. Thank you so much for that introduction. I'll just bring up my slides. Share. All right. Thank you so much for everyone for giving up your lunchtime and joining us today for a little bit of a talk. I'm taking you on a bit of a journey, as it says in the title, where I started and where I am right now. I think if I look back on where it started, you know, I'll go on to explain the slide in a minute. I would not have been able to guess that my career trajectory would have gone in this direction, and that I would have been in this privileged position to be, you know, living in this beautiful city, working with wonderful colleagues on some just fascinating science. But that's the world of science, right? That's the world of science and engineering. It takes you places, it takes you around the world. And specifically within our community, within nuclear, there are so many opportunities to work within the community around the world, and especially so in Australia, with lots of facilities and capabilities and people working in this sector. And I'm really, it's a real honour to be able to reach out to the women in nuclear community. Community is a big important thing to me, and it's just a really great opportunity for me to say hello, introduce you to where I come from, who I am, and hopefully we've got time towards the end to have a few questions. And so I'd really like to get to know you, and if you could say hello as well, that'd be great. So ANSTO Centre for Accelerator Science is where I am now. It's, as we said in the introduction, it's a research platform and a research user facility that supports research and industry communities to explore the past, understand the present, and design for the future. Towards the end of this talk, I'll give you a little bit of few examples of what we are doing within the platform to explain how that all maps together, and why I'm so excited and honoured to play a part and lead this incredible group of people working with fascinating bits of kit. But where it started, let's go right to the beginning. And again, as I said just now, if you'd asked me a few years ago if I would have guessed that I'd be here doing this job, I would not have believed you. I'd never planned my career out in that much detail. In fact, I think when I start off at school, I'd never even planned to be a physicist. Definitely didn't ever plan to go into research. I enjoyed physics at school. I chose to do physics at university, but I certainly never really envisioned myself within a career in nuclear or a career in physics. And I guess that's one of the reasons why I do lots of outreach. And if any of you also do lots of outreach to students and kids, like, this is the point of it, right? To show what a wonderful profession that we are. These are fantastic jobs, and we should be highlighting that because they're great jobs. We want more people to come and join us in this profession. And I know that if someone had come to my school or my college at that age and said, this is what you could do if you're even got a tiny inkling or interest in science and physics and nuclear, this is the place it can take you. I really would have really had this in my sights a lot more than I did at the time. So I'm very fortunate that the path I've taken has led me here, because it's a job that I do truly love. So where did it start? This is the first throwback photo. 16 years ago this month is when I started university. This is my matriculation photo. So matriculation is the process at the University of Oxford where you're introduced into the university. I was at Lady Margaret Hall College, which is a very well-known college for being one of the first to admit women into the University of Oxford. So it's a superb history. It used to be a female-only college. It's no longer anymore. It's a mixed college. It's got some really kind of famous people that have gone through those, very influential people in politics and literature that have gone through Lady Margaret Hall. So a fantastic place to learn and be part of the university environment. But matriculation is an interesting process where you enter this big grand hall. It's a bit like a graduation hall, a bit like it's a ceremony. They say something to you in Latin, and I don't know, I've never learned any Latin. It was something that I didn't go to one of those schools that had Latin in the curriculum, so I had no idea what I was signing up to, because I had to say something back. It was something along the lines of, I agree to be a part of the university, to honour the culture, and something like that. At least that's what they told me. But that happens in October time. That's the beginning of the term in the UK, and it's not actually, in the 19th of October today, it would have been about a week ago that happens. It's around the first or second week in October that matriculation happens in Oxford. So literally 16 years ago this month, I started off physics undergraduate degree at university. And 3 years later, that's when I had the first, I would say, real passion for a career, possibly a career in physics, because that's when I first discovered nuclear fusion. And this is going to be quite an honest talk, so this is my first bit of honesty. I did the 3-year degree. I didn't even do a master's because I was pretty fed up with physics at that point. The course was it was more of a theoretical physics course, mathematical physics, and that just really wasn't for me. I think I've always been part engineer, part physicist. I've always wanted to be much more on the applied side, being able to apply that knowledge to design something new, turn into something new. And so I'm always looking for applications, tangible applications of physics. And in my final year, my third year, I chose to do a kind of dissertation rather than an experimental project, and I chose the subject of nuclear fusion to discuss the benefits and challenges of that as an approach to a clean energy source for the future. And it really just lit a match in me, because I thought that was the best thing I'd ever heard. And again, I only heard it 3 years into my degree. It wasn't something that I'd come across any earlier than that, but I just thought it was fascinating, the combination of these really hot temperature plasmas, all the electric fields and magnetic fields all mixing, this beautiful nuclear process binding hydrogen together in order to release energy, yeah, bring a real potential to have a global impact on our energy ecosystem and the energy economy. So the whole thing just fantastic. And if any of you have been fortunate enough to involved in nuclear fusion research, or you've been to a nuclear fusion experiment, they really are just one of those jaw-dropping places in terms of the extremity of the engineering, the physics, and the goal. I mean, the goal of any nuclear fusion program is clean, limitless power for everybody around the world, based on a fuel that can be extracted from seawater. I mean, it's the stuff that like dreams are made of, right? In terms of physics. So yeah, that's what originally got the bug for me back for physics. And so I started to ask around some of my tutors at university who I knew were involved in fusion. And I started just asking a question. I thought, this is fantastic. Can you tell me anything more? What's going on? You know, what's the latest? And that's where I also was introduced to inertial confinement fusion, so that the laser initiated approach for fusion. And that kind of, I guess, inquisitive nature led me to the Rutherford Appleton Laboratory at the Harwell campus. So that was in 2008 that I started a summer 3-month placement. So if anyone has students that come over the summer, that's how I started. So I after I graduated my undergraduate degree, I went straight to Harwell campus, the Rutherford lab, to spend 3 months with the team that were working on laser fusion. And that was an extraordinary process. I mean, what an opportunity it was, because this campus is really buzzing. I mean, since 2008, in the last 12 years, actually, it's really expanded quite a lot. But at the heart of it was always the large research infrastructure, the synchrotron, the ISIS accelerator spallation, neutron and muon source, the central laser facility where I was working at. There's a lot of space research there now. There's a whole scientific computing department now. And then in and around that kind of government funded research labs is a whole suite of companies and businesses, startups, right through to big internationals that are all flocking to this site to be amongst this environment of researchers and scientists, innovators, people who are asking some of the biggest questions in the world, and some of those who are then applying that for new technology and new ideas that are making a tangible difference. So it was a fantastic place to be, and it was a great place to start off my kind of interest in what applied science and research looks like. So that 3-month summer placement was, as I said, within the central laser facility. It was my first introduction to kind of big science, big facility science, and I got hooked on petawatt lasers because I mean, who wouldn't? Because they're the most powerful lasers in the world. Fantastic machines, fantastic science that comes out of it, and exploratory physics as well as applied physics. So, of course, this is the Death Star. This is not a we're not supposed to talk about world most powerful lasers that are destructive in this form, but actually it's quite useful to show you this, because the parabolic focusing optic that you're seeing right now is exactly what we use in our laser systems when you focus these high powered lasers down to a tiny spot. we use a mirror that looks like that. And in some cases, the mirrors can be 1 meter wide. Sometimes they can be tens of centimeters wide. And that's the general principle, actually. In real life, petawatt and ultra high intensity lasers look a bit like this. So sorry to burst anyone's bubble. It's not a big black box with a big red button that says fire. The fire button actually is digital on most of these systems now, and it is pretty satisfying. Pressing fire, sitting there as an experimentalist, we get to sit within the control rooms. While we're carrying out the experiments, there's a countdown, there's sirens. It's very exciting. This is the Gemini Laser that is based at the Rutherford Lab at the Central Laser Facility. It's a ultra high power, so petawatt class laser, but it does that by delivering about 30 joules of energy in the infrared in about 30 femtoseconds. So ultra short pulse lasers containing a decent amount of energy in each pulse. That system will fire about once every 20 seconds, and the department in the CLF Central Laser Facility is now building a system that will have the same specification, a petawatt, but will fire 10 times a second. That's actually a new facility, the Extreme Photonics Application Centre, which is being built right now and is going to be coming online in 2024. So it's been very exciting. I've seen some of the photos, the build photos at the moment, and they've been going on for that, and it'd be very exciting when that opens up. I'm not a laser physicist, so sometimes people get a little bit confused when I say I'm a laser plasma physicist. So I'm a plasma physicist. I use this kind of laser to shoot things in order to study what happens when you shoot it and it turns into a plasma. So if anyone's got any questions about lasers, I can pass you on to the people that I'm afraid I never actually got involved with building the lasers. There was a whole team of people within our facility whose job and dedication is linked onto that. My role when I was a summer student right through to a PhD student and then on to kind of postdoc scientist was to build the experiments, apply for experimental time, do research and development. And this is what it looks like inside one of the chambers. This is a lovely illustration that an illustrative artist put together for us. It was a Women in Science Day, I think. And these huge chambers, vacuum chambers, where we position the optics for pointing the laser towards the target that you want to shoot. And just on the left-hand side here, you'll see that's one of those targets, that tiny little speck of, I think there's a gold foils actually. Those are the things that we shoot with the lasers. So that's the target in our experiments, and all of these mirrors and other diagnostics that surround that center. That's what you use to diagnose the plasma event by looking at the radiation, either photon radiation, X-rays, right through to particles, all the things that are blown off during an extreme laser solid interaction. That's what we use to diagnose and do our physics behind. So that's me as well. That's during my PhD, I think, actually. That must have been around 2010, 2011. So yeah, I'm an experimentalist, hands-on. I love getting hands-on right into the experiments, building stuff, and being my colleagues now will know that one of my favourite places is being in the control room, actually, especially being able to monitor the experiment as it happens and be right at the command centre. That's the bit I like of high-powered and big power facilities. So what does it look like when you shoot things with the most powerful laser in the world? This is a close-up photo of one of these target wheels that we use. It's about 5 centimeters wide for scale. And this is an overlaid photo. This is an SLR capture of the plasma emission coming from this zone. And this is what happens when a petawatt, that's 10 to the power of 15 watts, is focused down onto a solid foil. For those who know their laser intensity and irradiance, that's achieving more than 10 to the 18 watts per centimeter squared. So it's kind of equivalent to taking all of the sunlight that's shining down to the earth right now and focusing that down to the tip of a pen or a pinhead. So it's an extreme intensity of light that's delivered to an area very, very rapidly. This is where the photos get really cool. This is another laser plasma interaction. The laser is coming in from the top right-hand side and shoots onto the foil and produces this bright emission. That's the visible emission that we're seeing captured by the camera. But the diagnostic in this bottom left-hand side there, that's a proton pack. So it's actually a proton radiochromic film stack that's being able to monitor the particles, the protons that are being emitted from this zone. Because this thing that you're looking at, it's a laser plasma interaction, this bright burst of stuff that's about 2 to 3 times as hot as the center of the sun. It's extremely high temperature, but there's also some really quite extreme physics going on right now underneath all of this bright, beautiful glow. Using the extreme electric and magnetic fields of the laser pulse interacting with the electrons that are in the plasma in the target, you get these extreme Lorentz force interactions where now the electric field of the laser is causing those electrons to speed up. But so too is the magnetic field also having work done onto those electrons. So those electrons essentially in the plasma, they've gone from being part of the atoms of the target. As soon as the laser comes along, those electrons are liberated and you form this plasma of electrons and ions, and it's the electrons that then get whizzed up very quickly. They become very high temperature, they speed away very high speeds. And that's all because there's been an exchange of energy from the laser into the plasma. There's another force that comes into play. It's called the Ponderomotive Force. And what that does is essentially kicks out those electrons in the forward direction. 2 of those together, that is a miniature particle accelerator, because the speeds that those electrons get up to are approaching keV, MeV, so almost the speed, relativistic speeds. So just to summarize, the laser injects this high energy or high velocity pulse of electrons into the solid target. Those electrons will then escape very quickly from any type of solid that they started off with. As soon as they cross the target and vacuum interface, a really high charge separation sheath field is established, teravolts per meter. For anyone knows that they're accelerating fields, that's very, very high compared to any other accelerator that you can build in the solid state fashion, probably about 1 million times as strong as any of the best systems that we have in the world right now. And this essentially is what propels that beam of ions and protons forward with a very short pulse. It's a very quick burst of high energy protons and ions. At the same time, those high-speed electrons, as they whip through the solid target that you shoot, will generate in tandem a burst of bremsstrahling, high-energy mega-electron-volt X-rays that also come out with a quick flash. And if you're really clever and you place a little bit of capture material behind, you can catch the protons and ions to induce fission reactions in order to generate a bunch or a pulse of neutrons with high energy MeV at the same time. So this whole system here is really quite neat in delivering a supercharged but micro-sized particle accelerator. These are what we call the laser plasma accelerators. And it's a really bright emission. So this photo on here, the laser is coming from the right-hand side, interacting with a slab of, this is tantalum. And this bright emission is coming out on the other side. And that's because you're pushing out and punching out a whole bunch of energy in the form of particles as well as X-rays. And it's really bright. It's about 10 to the 12 particles per pulse. That's a very high dose in terms of protons and ions. And it's coming out very rapidly in a very short duration. And as I said, it's truly multimodal. You get the whole kit. If you want it, you can get X-rays, ions, neutrons, terahertz, if you're interested in that. And part of the field is actually being able to develop these accelerators so that you can control what comes out. Most of the time, we shoot and then we measure afterwards and we diagnose what comes out afterwards. But actually, part of the work that I did during my PhD and then through when I was a staff scientist in the Central Laser Facility was developing control mechanisms to be able to tweak change the emission in terms of the protons and the ions. I did this collaboratively with a lot of the universities in the UK. So my PhD was actually with the University of Strathclyde, and it was as a big collaborative grant with the Queen's University Belfast, the Imperial College London. And that collaboration, that kind of research family that we started in the UK, I stayed working and collaborating with them right through into my staff position at the Central Laser Facility as well. So I worked with lots of different mixed teams on extreme brightness proton acceleration, with the idea that you could apply this as a fusion igniter, utilizing isochoric heating, so being able to dump lots of high energy particles in a very short period of time, way before, much quicker than the material has time to expand and divulge energy and dissipate energy away, which means that you get something heated, but it stays at the same volume. So you get this high density and high temperature at the same time. And that's perfect if you want to set fire for a fusion reaction. And of course, as I said, neutron sources as well. This is a really kind of novel, compact way of generating short pulse neutron sources. I then, kind of later on in my staff scientist years, was then looking at developing point source X-rays and neutrons for high value manufacturing non-destructive inspection. That's because we found that the point source of those X-rays and neutrons meant that it gave very high spatial resolution for X-ray radiography. And on top of that, the X-rays are very high energy, which means they can penetrate through thick material, metals, high density things. So if you're working within nuclear, aerospace, automotive industry, and you want to be able to do high throughput inspection and imaging of large dense materials, these point X-ray sources from laser plasma accelerators are really the best thing out there, but they're still within the laboratory. So this is a picture on the left-hand side from a few years ago from the Vulcan laser target area. That thing on the left-hand side in blue, that's the vacuum chamber that I showed you the illustration of earlier. And the whole laser system, as I said, is on a national laboratory site. And now there are quite a few groups around Europe and the US now that are looking at being able to build a roadmap for commercialization of these sources. So how do you make the laser smaller? How do you make it turnkey operation so that we can actually exploit these plasma accelerators for science and industry applications? And that's where I kind of got into the bug of industry applications, innovation. I was involved in a patent that was filed. I worked with lots of companies in the UK people like Rolls-Royce and all these kind of big names that are really looking at low technology readiness technologies such as this for what's going to happen in the next generation. And that was a really interesting experience. I think that's the first bit of where I had experience that was beyond research and development, looking at actually that transition path to translating this research into something that could make a real tangible difference. That was really interesting, and I got a lot of experience, engagement experience, working with lots of people in different sectors, whilst continuing on my research experiments in the UK and across the world as well. Now, in terms of around the world, where to do these experiments, this is a map of low resolution, excuse that, from last year of all the ultra high intensity lasers around the world at the moment. So there's quite a few. Not all of them are to the high petawatt class. Some of them might be about 100 to 500 terawatts, but we call that petawatt class, so almost a petawatt. But you can see that you can do ultra high intensity laser plasma science with all of these facilities around the world. So an awful lot in UK and Europe and US, and lots of brand new facilities actually opening up across the Asia Pacific region. But as you'll see on this map, there's not many in the Southern Hemisphere. In fact, hardly any at all, none at all. And specifically down here, bottom right, and this is obviously a Euro-centric map, but bottom right, there's no high-powered lasers there. So when I saw that there was an opportunity, and again, linked through my networks and being kind of well connected on social, I think it's social, it must have been Twitter that I spotted it, that the Australian Institute of Physics were setting up a lectureship tour for a woman in working in physics. And I thought, what if I got that and I got to go across Australia and tell everybody about this wonderful laser plasma science, because there's a really good chance that a lot of the physics community, and certainly schools and general public, will have never heard of this, because it's not, you don't often hear about science that's not active in the country. Yeah, off I went and applied for that. And in 2018, that's what I did. So really privileged. Thank you, Australian Institute of Physics, for that fantastic, honestly, and literally life-changing experience, as you can see from where I am now. And it was truly wonderful. So 3.5 weeks in August 2018, 6 states, 35 talks. You do the maths, that's quite a few talks a day. I forget how many flights I took and how many hotels I stayed in, but it was a really great opportunity to meet the people across Australia, the research community. I visited a lot of the universities to give talks there, but obviously one of the most rewarding things was really talking to school kids. I did a lot of kind of girls in physics and talking to a lot of girls' schools. It wasn't all girls' schools that I went to. I went to mixed schools as well as state and private schools. So it was a really fantastic opportunity to just have an audience and reach out to people that there would no other way that I would have been able to reach out to these people, because I just don't know how they would have come across our tiny little research community of laser plasma accelerators. And so that was a really great opportunity, going across, started off in Tasmania, going across in Victoria, of course, across New South Wales, Canberra, this is Queensland, Toowoomba, I think this one was, and yeah, so getting to meet university groups as well, that was really great, and even got to go on TV. So I did a live interview with The World on ABC. That was at 10 p.m. at night. Let me just tell you, I have got time, I'm all right. This was such an I had many extreme days doing this talk, but this was phenomenal, because this is during the New South Wales bit. So I woke up in Sydney, drove down to Wollongong, got to Wollongong, did a 10 a.m. radio interview, and then went over and did a school talk, and then went over and went to the University of Wollongong and spoke to some of the physics department there and some of the research staff, which was lovely. We had lovely afternoon tea, and then I did a public lecture within, they had like a discovery centre in Wollongong, so that was a public talk, and then I was driven back to Sydney to get to the studio, ABC Studios, for 9:30 p.m. So it was quite extreme. And this was also what you call down the line. So I was in a little studio booth by myself. This is the first time I've been on TV, I have to say. I'm not a regular on the TV, but it was really extreme, but really great opportunity. So I just sat on a chair. Someone sat me on a chair, put one of those things in your ear, and said, look down this big lens. And this thing it's a good, like, yeah, 40 by 40, huge thing, looking down this lens in this darkened room. It's just the lens, that's all you have, no one else is in there. And they just said, oh, you'll be able to hear the presenter in your ear and just speak down the camera. And off we went. I think I was only due to be on a couple of minutes, but I think it's about 10 minutes later. She was really great, this presenter. She's really good at making me feel at ease, and if I couldn't even see her. So they just let me babble away, talking about high-powered lasers and the Women in Physics programme and all the wonderful people I've met in Australia. And so that was a really great opportunity as well. So again, adding all these things, if people give you an opportunity, it's very scary, but go for it, because it's great experience. Yeah, you'll learn and grow during the process, even if it's very excruciatingly uncomfortable. But it was, yeah, definitely one to say I can add to the CV now that I've done that. But one of the most valuable things, I have to say, was actually meeting the women in STEM networks across Australia. That really stuck out to me. There was a really strong community spirit within the women in STEM groups, particularly women in physics. And I had a really great time meeting people, kind of talking about people's journeys, learning from them, learning what they're doing in their local environments. Either this is the Flinders, this was the University of South Australia. This is an undergraduate women in STEM group. They're a really inspiring group of young women. Top left, that's a dinner in Melbourne with a physics group there, so fantastic. Some people might even recognise some of the faces there, some really great people. And obviously on the right hand side here is Jodie Bradbury, who's now president of the Australian Institute of Physics, fantastic host at ANU. So I had a really great time meeting that. And again, that's why it was a really fantastic opportunity. When someone said, come and speak to the women nuclear community, I was like, yes, please, because this is where it starts. You know, a lot of these people that I'm still in touch with now that in this position in Australia, which is fantastic. In fact, only yesterday, I was contacted by someone in RMIT in Melbourne because of some space research she's doing, and she remembers me from the tour, and now we got in touch. So it's fantastic that those connections are still alive. And of course, during 2018 was, as Patricia says, my first visit to ANSTO, Lucas Heights and the Clayton campuses as well. This is where I was able to have a tour of the site and see all the national lab facilities on those Harwell sites and give my talk, Dream Beams, Laser-Driven Inspection Technology for Medical, Nuclear and Aerospace Applications. It's also where I first toured the Centre for Accelerator Science and had this photo here in front of the Antares Accelerator. And yeah, I cherish this photo because you can see I'm very, very smiley. But another story, I woke up in Hobart on this day, got the first flight out to Sydney, toured all the way around ANSTO, and then got a flight in the evening to Perth. It's a really long day, but I was still very happy to be there. And having worked on laser plasma accelerators for proton acceleration for my whole research career up to now, you know, I've not had chance to work with these kind of solid state RF and electrostatic accelerators. And so walking in and seeing one of these, because they really are quite huge, and I've only worked with proton accelerators that come from a tiny little foil and a huge a laser. So this was a really good opportunity, and I think I went in there and said, "Can someone please take me a photo?" I didn't ever appreciate that actually the heritage of this system is an original Van de Graaff. And I've only known Van de Graaffs in those little demos that you have in a physics class where you wind up the coil and the chain, and you can use it to make your hair stand on end. So I did not appreciate that Van de Graaff was a electrostatic accelerator manufacturer. So that's another reason why I had that photo done, which is I think it's quite to the amusement of some of my colleagues now. So then I went back to the UK and started as the group leader for the laser department's industry partnerships and innovation group. So there's a group of us here. We're kind of industry facing scientists with lots of different expertise. Helen on the left hand side here is actually an illustrative artist in her background, and she was the impact and engagement officer for the department. She's one of the first people that I recruited in, actually, and I was really proud of that because she didn't have a science background, but she's still there. She's just been promoted this year, actually. So fantastic person to bring into science, because her perspective, her outsider perspective, is really valuable. And then Chris Thornton was linked with a couple of big industry companies within the UK, applying laser-driven plasma accelerators for inspection. So Johnson Matthey is one of the biggest manufacturers of chemicals in the world. And these manufacturing technology centres were involved in high-value manufacturing. And then Catherine Wellesby was a microscopy and spectroscopy specialist, looking at physical chemistry and applying that for lots of different companies as well. So it was a really good time to be part of that team. Multidisciplinary, so again, my first opportunity, again, that was an opportunity that I kind of grabbed with two hands, a little bit different than I'd ever done before, but a really great opportunity to grow and expand my repertoire, my experience, and of course, a little bit uncomfortable at the start, but you get to learn things and you get to step outside the box. It's the first time, again, I'd stepped outside of laser plasmas and looked at other different applications of the lasers around me. And then, no surprises, the next big step I did when the opportunity arose was to come and join ANSTO, home of Australia's landmark research infrastructure, and move over to New South Wales, over to Sydney, and start life at the Lucas Heights campus. So when this job opportunity opened up, it was something that a network, a kind of a close friend of mine actually put me in touch with and said, look, you should give it a go. I think it might be something that you'll be interested in. And I'm really glad that I took the jump, because it is a fantastic place to be. Now working within this environment, again, big beam lines and experiments, that's where I really like to be involved in those kind of groups. And what we do now, again, being a community-focused person, that's what I really believe that one of the values that we have within the Centre for Accelerator Science is providing support for the research and industry communities by opening up and making use of our ultra-sensitive analysis techniques. So we have a really diverse suite of radioisotope dating, trace element and actinide isotope analysis. And these techniques are world-leading in terms of sensitivity. We can really count individual isotopes at a time. So that's what you get when you apply accelerator mass spectrometry and ion beam analysis. You get that really high sensitivity and being able to look at very tiny amounts of radioisotopes and elements that are within samples. So it's a fantastic set of equipment for analysis and characterization, and we have people from all over the world come and use it. Accelerators, ion beam accelerators, can also give you precision irradiation. So it can give you implantation and irradiation capability. So you can do surface engineering as well as characterization with micron resolution. And we also have a program that delivers rapid radiation exposure and damage so that you can do materials testing. But one of our most valuable assets, I guess, is our people and our end-to-end user provision. So the fact that people come to us with an idea and we'll support them in designing an experiment, applying for time, and then interpreting and analysing the data that comes out of it, so that we hold people's hands all the way through, right through from idea through that full journey from idea through to impact. And of course, being a good research infrastructure platform, we provide these training and networking opportunities and environments so that we can make sure we skill people up, either that's next generation or it's our own staff or our collaborators, in these quite niche skills, but actually very important skills for impact. We are Australia's largest user facility for ion beam accelerator applications. And this is a photo of the team that was took earlier this year. One of our first gatherings that I was able to do after I started. We have a whole team of, as I said, scientists and engineers covering all different aspects and supporting climate, environment, and earth sciences, nuclear safeguards and forensics, advanced materials development, as well as cultural heritage. And I've got some examples coming up now of some of the work that we do. Being Australia's largest facility, what does that mean? That means that we have lots of accelerators, and we have lots of people and lots of users. So 37 experts in our group, full-time staff. We have about 350 users that come to us each year. We have 12 sample laboratories and 4 accelerators across 12 beam lines. So we're quite a big group of expertise with lots of diverse capabilities. One of the wonderful things that I've really got to learn, and again, this is because I'd never been involved in accelerator mass spectrometry or involved in chemistry behind the sample preparations. It's been a really good learning experience for me to understand some of the expertise that we have in extracting and handling cosmogenic and actinide isotopes from these samples. And there's all sorts of things that come into our department, and it can be rock, ice, sediment, bits of fibers and filters, pollen, corals, bone, you name it. That's what comes in at the beginning, and at the end it ends up with this tiny little solid kind of target that goes into the accelerator wheel, and that's what we analyze and we use for the radioisotope dating. So it's a really great team of people that can take that sample from its raw initial state, right, to take it through all those chemistry steps in order to get into a pure solid state at the end, and that we can use for measurements. And this is just some of the examples that we've had from a recent ANSTO PhD student who was extracting collagen from Neolithic human teeth ahead of being able to radiocarbon date it, which is quite, I took my breath away when I saw that. I actually went to see Charlie in the lab. He was working on the chemistry behind it, and I got to see these little teeth, and yeah, quite extraordinary. But it was wonderful that Charlie was happy to go on record to say that the expertise and experience of the people were the most valuable part. And I have to say, here, it's honestly a wonderful group of people. And this is another PhD student that has now sat in the control room. It's one of, as I said, my favorite places, working on our Vega accelerator, counting plutonium-244 isotope particles within samples that come from the bottom of the Pacific Ocean, because he's using that as a 10 million year time profile of interstellar influx to Earth, mapped through looking at iron 60 and plutonium-244. So being able to explore the astrophysical origins of the nuclear synthesis processes in supernovas and remnants by looking at what's available to us right here on Earth, right at the bottom of the ocean, being able to take that sample and then process it, put it in the accelerators, and they're counting one by one on the screens behind them the plutonium-244 ions that are in that sample, and that gives them an indication of some of the physics from where those come from. And on the same day that I took that photo, I turned around in the control room, and on the other side of the room was a group of UNSW honours students who were here to implant specific ions of exotic elements into materials, because they were studying that as a process to enhance the performance of catalysts in future battery systems. So this is advanced materials fabrication in action, looking at what happens when you dope or specifically deposit ions one by one into these materials in a very controlled and design manner. Another PhD student that we've got working on a similar process in implanting metallic ions is for low energy electronics implantation into topological insulators. So really kind of, this is when I talk about, you know, designing solutions for the future, this really is like green technologies start with being able to fabricate designer materials, and that's what ion implantation is. And just to give you an example of some of the other wonderful questions and research that's going on, we've just welcomed recently a cohort of ANSTO-funded PhD students and early career researchers who will be coming to the lab for various parts of their project to study all sorts of things from in the past climate, past environments. So again, this is this thing about exploring the past, looking at environmental and ecosystems in the past by looking at the samples and digging them up and being able to date them, right through to being able to look at present day conditions and being able to monitor environmental systems and water resources, as well as right through designing materials for the future. So it gives you a nice snapshot of some of the extraordinary range of science and research that we can do with these accelerators. And I'm going to wrap up really quickly now, actually. So just another example of one of those, what happens from the journey of idea to impact. It was a really nice story engagement that we've had in being able to date Aboriginal rock art in the Kimberley region that doesn't contain carbon. So normally you would have to extract carbon to do radiocarbon dating, but instead of, there's no carbon within the rock art pigment itself. So instead, a collaboration with the University of Melbourne and the traditional owners in the Kimberley, as well as University of Western Australia, collaborated with us, being able to date not the art and pigment itself, but the wasp nests that they observed to be underlaying and overlaying the rock art that give kind of boundary conditions of the upper and lower dates of the art itself. And they found that it was over 17,500 years old, which is the oldest painting so far reported in Australia. And in terms of impact, this wonderful quote here from Ian Weiner, shown here on the left-hand side, is traditional owner and Queenie man involved in the field work and research for this, saying that What we've done now with the scientists is open up the gate to find out how old their paintings are. It's an important part for their cultural history and acknowledgement of peoples that have been before them. So a really important part. And again, an ANSTO PhD student was involved in that process, really looking forward, and came here because of our world-class capability for measuring tiny amounts of carbon. We're also involved in an air pollution monitoring network, which is a huge environmental impact that we have, being able to monitor the pollutants within the air, being able to tell what they are, and also tell what their concentration is, which is a really important thing, being able to look at how air pollution has changed over the last few decades, and also how it's affected right now with various different events that go on. And now we're applying that for being able to look and support accreditation of native plants, specifically here the Kakadu plum, being able to prove that it was came from the region that it came from, being able to use these same elemental fingerprinting techniques that ion beam accelerators give us. And looking to the future, we've joined the National Space Qualification Network, applying our ions in order to mimic space radiation, so that you can test electronics before they go into space to check if they'll survive or not. So that's a really new thing we've just started. And we've just opened Australia's first ion beam radiobiology beam line, which is a really fantastic new step that we've had very recently. And what that opens up is capability for ion beam radiobiology to look at the biological effectiveness of heavy ion and proton irradiation on cells. This is a photo of stained cells demonstrating double DNA strand breaks that shows that actually the proton and ion irradiation had a damaging effect on the cells. It's a very important thing for understanding for space missions in the future, when we want to be able to explore and go to Mars, but also looking at developing new and advanced methods for proton beam treatment here on Earth. So with that, thank you very much for listening. I'm really excited to be part of this community even more. Here in Australia, we have the National Collaboration for Research Infrastructure Strategy. It's a huge collaboration of facilities across Australia. It's a fantastic community to be a part of. This is a photo of myself and Matt Riley, who's the Director for Climate and Atmospheric Science within the New South Wales government. And I just had a meeting with him this morning, actually, talking about how to develop our partnership further. And this is myself with the ANU Heavy Ion Accelerator Facilities, so another new community of Accelerator Science people in Australia that I look forward to develop. I'll just leave this here for the questions. This is just a bit of, I guess, like words of wisdom, I guess, that I tend to live by, and I do advise to others about developing your network, having aspiration, but also being mindful. So this bit here, it's not just who you know, is who knows you. There's a slight difference of being able to make sure that you do something and form solid and honest relationships with people, so that you can support each other throughout your career. Outreaching, really important for broadening your viewpoint, but also making you very visible. Aspiration, seeking out opportunities for growth and be strategic. So, doing things that feel a little bit scary and uncomfortable. That's actually the most exciting when you jump into those. And then be mindful. So think about your career and what works with you for your social and life plans. Be aware of anxiety and mental health conditions, and also what you can do to support yourself and others. And then be aware that in our field, in nuclear science, but also just engineering and research in general, failure is inevitable, but it's also an opportunity. But let's not ignore that it can be painful. So yes, resilience is probably a good core skill for anyone in our field. Thank you so much for listening, and I'm sorry I've got a bit over time. I hope there's a bit of time at the end to get some questions going. But if not, then I haven't put my email on here, but I can drop my email in the chat if anyone wants to get in touch. And when we're open, I will have you all over. So all come round to Lucas Heights, and I'll show you around the Centre for Accelerator Science.
Thank you so much, Ceri. What a journey you've had, and looks like you have exciting things for the future as well. This question has been in the chat function for a while, so I'll quickly ask this. How much of the functions of research reactors can laser plasma replace?
Yeah, that's an interesting question, because it probably comes down to the neutron generation. And that's an interesting conversation to have. We did start to have that conversation a bit with the ISIS neutron source. That is an accelerator spallation source, not a reactor source. So the specifications of the neutron beam lines are slightly different, but they're looking to the future of future neutron sources, and they're looking at how laser plasma accelerators could contribute to that. The brightness, or the flux, or the neutrons per second, I don't think you'll ever even get close to a traditional accelerator spallation source with laser plasmas. So we're absolutely nowhere in the field of the intensity and average brightness and concentration from a reactor in terms of using neutrons from a reactor. There are some applications where there is a niche, though, and that's if you need ultra short pulse, laser plasma accelerators are the one to go. So for some science applications with neutrons, the laser ultra short probe, I think, is an advantage. If you want a compact, deployable, dare I say, portable neutron source, laser plasma accelerators could be one for the future. We used to use the word deployable rather than portable, because portable neutron sources, DT fusion those tubes, they're fantastic. Really high brightness, great. They do the job, work really well, and they're really quite compact. Laser plasma accelerators are not going to get to the size of a tabletop, but there are plans to try and get them down to the size of a small crate, a small container. So they're a deployable system, so I think there'll be some areas that laser plasma neutron sources could really open up science applications, maybe some of the inspection and imaging in nuclear forensics, if you want to be able to probe things and be able to look at very short lifetime nuclear signatures. A laser-driven neutron source with a picosecond duration, you'll be able to resolve those short lifetime nuclear signatures with a laser-driven source. But for irradiation purposes, it wouldn't make good commercial sense to use the laser plasma at the moment.
Thank you so much. We might have to wrap it up. Thank you, everyone, for joining us. Please keep the conversation going on our socials. And WiN Australia thanks our sponsors for their ongoing support. And thank you again, Ceri. That was an amazing talk. Yeah.